Just 16 million years ago, the volcanoes that created Iceland emerged from the sea, many of them just like the explosive appearance of Surtsey from beneath the waves in 1964. So much lava has been erupted that by now a mountain of basalt over 10 kilometers high would have formed. But Iceland stands on top of the Atlantic spreading ridge, and it's splitting apart. Chains of submarine mountains mark the positions of the ocean ridges worldwide. The pink spots are earthquake epicenters, often associated with submarine volcanic eruptions along ocean ridges and subduction zones. The bend in the coastlines of Africa and South America are associated with a large transform offset on the Atlantic ridge, the Romanche fracture zone. Similar, less extensive displacements are seen on other transforms further north. And the zone just south of the Azores has been studied in detail by manned submersibles. Here the ridge takes the form of a large rift valley with subdued hills, each the site of a volcano. The yellow material is a zone of vertical, sheet-like bodies of magma, known as dikes, through which magma rises from a chamber below. A typical eruption starts with earthquakes and drifting, and several volcanoes build up along the rift. Each new eruption starts as a dike of fresh magma rises through the rift, producing volcanic lavas above. Over a period of months, the volcano deflates and activity wanes. The volcano and its feeder dikes are spreading to the left, and others form in the center. And after about 30,000 years, the early volcano is now several kilometers to the west, on the edge of the median rift. So the activity on ocean ridges is essentially that of volcanism associated with rifting. To study the processes more intimately, we need ocean crust exposed on land, and almost at the northern limit of the mid-Atlantic ridge, a particularly active zone has raised the seabed, creating Iceland. The ridge is marked by a line of active fissures running from the southwest to the north right across the island. Today it's a basalt landscape, a land of ice, a land of fire, a land of water. And here at Krafla, there's no doubt that I'm standing on hot ground. Beneath my feet, steam temperatures of 340 degrees centigrade have been measured at just 2 kilometers depth. And that's about 10 times higher than average. Now all this is caused because there's hot magma at just a few kilometers greater depth. In fact, there's magma underneath the whole of the Icelandic spreading ridge. Sometimes it's erupted at the surface, here about every 200 or 300 years. And it's the interaction of hot magma with groundwater under normal conditions that keeps this geothermal field active. Sizzling steam pools, boiling hot mud pots, and spatter cones are common in areas where the steam emerges quietly at relatively low temperatures and pressure. But that's not what happens at Geysir. Superheated steam from 4 kilometers depth jets up every 7 minutes or so, and cooler steam takes its place from the surroundings as water continues to seep down from the surface. However inviting, this is one pool I wouldn't step into. The magma underlying all this geothermal activity is often suddenly released in spectacular volcanic eruptions. This is Krafla, northern Iceland in August 1984. A fissure several kilometers long has been active intermittently since the mid-1970s. Occasionally erupting glowing fountains of basalt at over 1,000 degrees Celsius. An almost continuous wall of lava, just part of an 80-kilometer long fissure swarm. This massive upwelling of magma has already added half a cubic kilometer of new lava since 1975. The rift here has widened by 4 meters in less than 10 years, and yet on average Iceland is splitting apart by 2 centimeters per year. 2 years since the last eruption, this is still a hot, steamy and sulfurous place. So this fissure, part of the Krafla fissure swarm, marks the position of the mid-Atlantic ridge on land in Iceland. Black basalt lava has been erupted from this fissure several times during the last 12 years. Lava's flowed away from the fissure with speeds up to an incredible 40 meters per second. And fire fountains built up scoria cones like this that mark the line of the spreading ridge. And this is a tongue of one of the new lavas, and its source is here in this small fissure, which is about 100 meters away from the main line of the spreading ridge. Now, I've climbed up to the top of a spatter cone that was formed in 1724, and the lava has flowed down through this spatter cone and has breached one of its walls. The junction between these two lavas, then, represents a time gap of about 250 years, and it reminds us that seafloor spreading is rather a spasmodic process. And just to reinforce that point, here you may be able to see three ages of lavas, from the oldest and most weathered, the lightest coloured at the bottom, through two lavas that have flowed around the spatter cone, the medium grey, to the youngest and blackest basalt at the top. Well, I've now come down to the southwest of Iceland, and there's more evidence here for the jerky nature of seafloor spreading. Unlike Krafla, which has been active quite a lot in the last 10 or 15 years, the last lavas erupted here were 2,000 years ago. But still, Iceland's being torn apart, and evidence of that is this fissure I'm standing in. It's a crack in the ground which is about 10 meters wide. It goes down to about 20 or 30 meters deep, and it's filled with cold glacial water. Next time magma rises up underneath this area, it may well fill this fissure, and it may form a dike. Now, fissures like this mark the line of the ocean ridge as it spreads away down through to the southwest of Iceland, and here it forms a huge rift valley. The valley's called Thingvellir, and it's the site of Europe's oldest parliament, the Althing, which was established here in 930 AD. The Icelandic parliament continued to meet here for about 8 centuries after that date. Now, I believe that this is one of the world's finest rift valleys. Well, this is a pretty unique place. It's the kind of thing rarely seen on land, and what I'm doing is standing in the western edge of the rift as it runs through Thingvellir. Now, what we've got here is a 20-meter high cliff of basalt lava flows, and they're the kind of thing which forms the upper layer of the ocean crust, seen here on land. The important thing about this cliff is it parallels in miniature the kind of rift zone that occurs in the axial spreading ridge of normal ocean crust. But since these basalt lava flows have been formed in this place, there's been a central collapse of the rift. Well, I've now climbed part-way up the rift walls, and I'm standing on top of the 9,000-year-old lava sequence. Now, you can appreciate how complex the faulting system is here, because the faults down towards the valley have actually downfaulted about 10 meters more than the main faults on the rift margin, and this means that the whole of this block has been rotated as the faulting has occurred. Well, I've now climbed up to the top of the western edge of the rift, and you can see the rotated blocks down there rather nicely. And if we follow the Thingvellir Rift Valley with its fissures way up to the north, you can see the classic dome-shaped shield volcano Skjaldbreiðar. Now, volcanoes like that are important to us because they give us information about when they were formed. That kind of volcano can only be formed since the ice was removed from this area about 10,000 years ago, because the lavas that form the carapace, basaltic lavas, have to be relatively free-flowing to form a shield volcano. But there's another kind of volcano over on the eastern edge of the rift. And looking over here is Hrafnaborg. It's a table mountain. And that kind of volcano can only have formed under the ice. The Rift Valley is about 5 kilometers wide, and it has similar faults on the other side. But further south, down in the southern end of the main rift, we've got this spectacular lake, Thingvallavatn, which is about 10 kilometres long and about 5 kilometres wide. It's the largest lake in Iceland, and if you follow the line of fissures way down to the south, there's a geothermal area on the northern slopes of a large central volcano, which in fact dams up the southern end of the lake. So this is the central volcano Hengil, and although the last magmatic activity here was 2,000 years ago, most obvious features today are the geothermal plumes on top of boreholes that have been sunk 2 kilometres down to find geothermal steam, and soon there'll be a power station here. Now, Hengil itself is dormant, but it's had a long history of activity, very complex history, and it's given rise to lavas that have flowed north into the lake. And over here, we can see a steppe topography in the lavas on the edge of the rift as it goes north of Hengil. These steppes are little fault scarps. But moving around to the north, we can see a very good view right the way down the Thingvellir Valley. And remember, the important thing about this valley is that it was probably a great big arch pre-10,000 years ago. The arch would have been formed by magma coming up underneath. And of course, since then, there has been collapse as the magma's drained out. Now, the most recent activity has taken place in a line of scoria cones, which are those little mountains over there, through the line of islands and away to Skolbreiðir in the north. That happened 2,000 years ago, and what we're looking at there is a dike system that connects Hengil through the scoria cones, through the islands, right out to Skolbreiðir. A dike system which has occasionally hit the surface and has erupted small cones. And if I was asked to predict where the next activity might be along this part of the rift, then it would probably be along that line, connecting right up with the shield volcano Skolbreiðir in the north. How did this shape arise? Well, activity usually starts from a single vent, forming a thin pancake of black basalt lava kilometres wide. As further eruptions occur, a thick pile of successive lava flows build up the characteristic domed shape we call a shield volcano. It may not look impressive, but the amount of lava was enormous. If it had erupted during the Ice Age, the lava would have been confined, and it would have built up a table mountain like this. Herdebrid, the majestic queen of Icelandic mountains with its characteristic sheer-sided flat-topped profile. 10,000 years ago, Iceland was still covered by massive ice sheets, and today a few small ones remain. But the volcanic activity which had created Iceland continued unabated. At first, the magma melts the ice, forming great subglacial lakes. The overlying ice fractures and collapses. The lavas are chilled by the icy water, forming pillow-like structures pointing away from the vent. In 1971, Dr. James Moore swam right up to this advancing lava flow of the Kilauea volcano in Hawaii. The chilled outer surface forms a tube through which the molten lava is squeezed out like a tube of toothpaste. So millions of years later, when a geologist sees a section like this, he can be sure that it was formed underwater. Notice the crystallized rock interior inside the smooth vitreous crust. In Iceland, most of these pillow lavas can be dated and are known to have formed during the last ice age. And the time gap between these lava tubes must have been several days, if not years. But the overwhelming pressure of water has absorbed the volcanic gases so that neat piles of pillow lava form like building blocks. Submarine lavas several kilometers down on the ocean floor are known to have pillow-like shapes. But to determine the deeper structure of the ocean crust requires information from seismic studies, coupled with geological observations of fragments of ocean crust exposed at different levels. Here, in the deeply eroded volcanic structure of the Atlantic island of Madeira, are networks of dikes, cutting up through earlier volcanic ashes and lavas to feed younger lava flows above. The lowermost rocks of ocean crust are coarsely crystalline gabbros and periddotites. The gabbros are the slowly cooled, crystallized, and non-erupted parts of the magma chamber, while the peridotite form the base of the chamber and the underlying mantle, from which both gabbros and basalts are generated by partial melting. This kind of broad structure is thought to underlie all ocean crustal areas, including Iceland. You can see that melting in the mantle provides magmas that supply the storage chamber above. Periodically, during rifting, magma rises through vertical fissures to form the pillow lavas above. And in Iceland, there's a striking difference in structure where basaltic eruptions formed simple lava flows with no water involved. Remember that pillow lavas formed under the ice produce the foundations of table mountains. But now, as the eruption rate increases and the ice melts, the lava forms stratified layers called hyaloclastites. This small piece of hyaloclastite basalt rock is made up of small fragments of yellow devitrified glass. It's loosely compacted, but still chemically the same as the black basalt pillow lavas beneath. As magma continues to flow, the vents grow thicker and layers of confined lava gradually build up the volcano until it rises above the ice cap and forms a small cone of ash, before finally the eruption stops. When at last the ice age ends, the dramatic profile of a table mountain is exposed, but rock slides and erosion rapidly soften the outline. Table mountains can form rapidly in hundreds or thousands of years, but to make a massive central volcano like Hengil needs over tens of thousands of years of almost continuous activity. So it's not surprising to discover that table mountains lie deep inside the core. They're the nucleus of a central volcano. After the ice has gone, a massive central eruption may completely cover the core, and later events, kilometers apart, broaden the outline. The end result is an overlapping sequence of separate volcanic vents, fed from one large, upwelling, deep magma chamber. The complex history of Hengil is poorly understood, but right in the center of Iceland's rift zone, in magnificent isolation, stands the most famous central volcano of all. Surrounded by its own ash desert, the great caldera of Askja covers an area of 45 square kilometers. Only from the air can you really appreciate the full extent of the caldera. It originally collapsed in a circle along ring fractures, but now it looks more like a skull, with the brilliant blue of Lake Oskjuvatn to the south, and the breach in the caldera wall to the northeast. Since the caldera formed, there have been many eruptions into the circular depression, which have covered the floor with a great thickness of lava. In 1922, a stream of lava emerged from high up the east wall and flowed into the lake. In the lake itself, there have often been signs of activity. For example, a small volcano formed an island in 1926. But perhaps the most spectacular event was the large explosive eruption which created a line of explosion craters across the lake, one of which is preserved today as the crater Viti, Icelandic for the mouth of hell. It happened one cold winter's night in March 1875, and water upwelling into Viti is still hot from the magma below. The lavas and pyroclastic rocks forming the walls of Viti tell of older explosive events and lava flows in the history of Askja. Just imagine what the original volcano must have been like. Before the large caldera formed some 5,000 years ago, a large volcanic mountain of subglacial hyaloclastites and subaerial lavas must have dominated the landscape. Remember that, like Hengil, Askja is a central volcano which has evolved slowly through a long series of volcanic events. But the central core has collapsed. In section, you can see near-vertical circular fractures that formed after an eruption as the pressure of subsurface magma was released, causing subsidence. New vents form as upwelling lava creates flows, an island in the lake, explosive cones and craters. And here, high up on the east ridge of Askja volcano's caldera, in the summer of 1986, a group of us from the Open University are measuring various geophysical parameters that are helping us to understand the volcano. This is our station ER10, East Ridge 10, and it's already been measured for elevation. We know the elevation of this point through various surveying techniques to a fraction of a centimetre. Now, this particular instrument is a gravitymeter. It's a very sensitive spring balance, and we're using it to measure the strength of the Earth's gravitational field here. The instrument could actually measure the difference in gravity between where it is and, say, my feet. What we're using this instrument for is to find out about changes in the density of rocks under the ground, because those changes in density cause variations in the acceleration due to gravity. But more important still, if magma was to rise underneath the system, then there would be rapid changes of density that would be measurable using a gravitymeter. So we want to monitor the gravity field to see if we can predict when the next eruption might take place. When an entirely new volcano erupts under the sea and activity continues beyond the initial explosive phase to form an island like Surtsey, there is little effect on human lives. But when a long-dormant volcano on an inhabited island suddenly bursts into life, the consequences can be disastrous. Well, I've now come down to the very southernmost tip of the eastern spreading rift zone as it passes south through Iceland, and I'm in the Vestman Islands. And this is actually one of the most active parts of the Iceland spreading centre. Surtsey erupted in 1963, and behind me the large mountain is Eldfell, which was active in 1973. It was a huge scoria cone which built up by fire fountaining and then became breached on its northwestern margin to form a lava flow, which we can see coming through a narrow channel and forming rather hummocky ground, which has collapsed over here, and then gradually widening out. But as it widened out, we see the lava front almost blocked the harbour that exists between the lava front and the older mountains behind. But fortunately, thanks to various spraying efforts with cold water, the lava stopped, and that actually created a much better fishing harbour for the largest island in the Vestmans, Jaime. But there were other advantages too, like the large amount of new land that was created, like the amount of scoria that was available for building materials, which just hadn't been there before, and also the amount of heat that was present in the lava that could be exploited. Well, I've now come to the base of Eldfell, and I'm standing on the 1973 lava, which here is being exploited for its heat. Cold water is being pumped into the ground, and hot water brought back from about 40 meters depth, hot water at 50 degrees centigrade, which is then sent through these pipes to the town and is used for space heating in houses. Now, this is really a rather low temperature use of geothermal energy, but elsewhere in Iceland there are high temperature zones where geothermal power is being produced. Pipes like this, linked to 8 boreholes, produce high-pressure, superheated steam from about 2,000 meters depth. And they all go to Krafla power station, the largest in Iceland, which produces 30 megawatts. That's enough to heat about 30,000 homes, a sizable town. But it's been estimated that something like 3,500 megawatts could be produced along the Icelandic ridge if the Icelanders wanted it. But sometimes there's a catch. In 1977, after they drilled a geothermal borehole here to tap the high-pressure steam, suddenly a mini-volcano, Iceland's smallest, burst out of the pipe, erupting 3 tons of glassy cinders in just 20 minutes. And that's the problem of exploiting geothermal energy on an oceanic spreading ridge.